Okay, so we can start now. It's 6 p.m. Today we are in the week 7, Introduction to Material Science and Engineering courses. So we have already went through the video that was given by the Professor Rajesh Prasad. Now we'll just quickly try to have a recap that what are the rest of the topic that has been covered, and then we'll try to solve your doubt if you have any, and then we'll move towards the Q&A, question and answers. So yeah, feel free to interact with me. You can always like if you are comfortable, you can unmute yourself, and whenever you face doubt, you can have an interaction with me. Okay. So the list of the topic that has been covered in this particular week, week 7, is as follow. We discuss about the phase diagram. What is phase diagram? What information does it give? What are the phases and what are the components? That are the two important things that we have learned in the phase diagram. How we can use the phase diagram? In what way we can extract the information? For example, we have studied about the composition of the phases that is present in the phases present in the system, how we can identify properties of the phases in the systems, microstructure evolution during solidification. So we saw that there was an isomorphous diagram in which a liquid is there and it is converting towards the solid. So liquid is converting towards the solid. So how the microstructure is changing? So initially we saw that entirely it will be liquid, and then at the end we saw that a grains will be formed and it will be the crystalline solid. So this evolution we have discussed. We discussed about the eutectic system and also eutectic reaction. Eutectic is a point, it's a composition at which we get the low melting point will be lowest. Okay,
Sir, can you explain that topic in with detail? That
sure. We'll discuss about the eutectic system and eutectic reaction. Let's go with that. For example, I will take a general one diagram. I have on the y-axis we have temperature. On the x-axis we have composition. We have two components. Let's say it is made up of the A and B. So if we are moving along the x-axis, we will see that we are varying the weight percent of B. So depending upon that, our phase will evolve. Let's say the melting point of A is something. TA is the melting point of somewhere over here. TB will be the melting point of B. We can mark somewhere over here. Okay. And now we can make a reaction, eutectic reaction. Above this particular line, liquidus line, we'll get the liquid. Let's say the composition, the phase which is rich in the A, it's alpha, and the phase which is rich in B is a beta. In between, we know what we will get. We'll get in between liquid and beta, we'll get alpha, sorry, beta plus liquid. Alpha and liquid will get in between, we'll get alpha and liquid. And here, it will be the mixture of alpha plus beta. Now, we know that this is the melting point of pure metal A, pure metal B, let's say, and it's a melting point of pure metal A. This is the melting point. What's the melting point of, let's say, this is at the composition 10. 10 I am specifying with like the 10 weight percent of the beta, 10 weight percent of B, so on and so forth. Here, let's say I am specifying the 50. So now our aim is to discuss about the eutectic system. This is a eutectic system where we can see if I try to draw the line, if I try to draw a border where liquid is forming, like above which only the liquid will be there, so it will be like this. Eutectic point is a composition where we'll get the lowest melting point. So what do you think? Where we are getting the lowest melting point? It is the pure A or pure B or at the 10 weight percent or at the 50 weight percent? Which one is giving the lowest melting point among all of them?
At 50 percentage.
Yeah, at 50. So if I take the composition, if I take A and B and I mix them in the 50-50 weight percent, then I have to heat the temperature which I have to provide to melt the system will be the lowest. If instead of 50 I go with the 40, then melting point, the point at which the entire system will convert to the liquid, the temperature will be higher. So eutectic system is given by this. So what we can say here, at this particular point, if I have only liquid, let's say, now I am cooling the system at 58%. So liquid is there. It is giving me alpha and beta. This is my eutectic. Okay, so now what is happening here? I had a phase initially at high temperature, let's say temperature this particular, I will point it as 1. Initially we had only liquid. Now once we came just below this particular point, just below this temperature, let's say somewhere over here, just below the eutectic temperature, I am denoting the eutectic temperature as, let's say, TE. When we are just below TE, we can see that here the phase will transform, and the phase will transform to the alpha and beta phase. So now liquid which was there, it is converting to the solid, and it is consisting of the alpha plus beta. While if I take any other, let me point it at, this is the TE. Now if I take any other line other than 1, other than this particular composition, let's say I'm taking at the 10, what is happening? In this case, liquid was there, it is transforming to the alpha, it is giving rise to alpha and liquid. Here we have the liquid and alpha, and then it's further going, like further it will go to the transition where it will form the, this is the before the eutectic reaction, then again this liquid will form alpha plus beta mixture. So this step which was there in all the other composition or in all the other point, that we are avoiding, and we are able to get from liquid directly alpha and beta. Now why we are calling as an invariant? Why we are calling it as an invariant? Invariant means it's not variable. What it's saying that the temperature and the composition, let's say composition, I'm denoting by the C. Okay, this composition, they are not going to change. Now let's apply the Gibbs phase rule which we have learned. This is a Gibbs phase rule which we have learned. We know when we are talking about the phase diagram in this present case, this 2 is represented as the is for the temperature and as well as for the pressure. Pressure will remain constant, so what we can do for the phase diagram, the pressure we are not taking into the consideration, the pressure is constant. So the P plus F will be equal to C plus 1. We know the number of components are A and B. The number of component is 2. Don't get confused, let me write it as B. This is the number of components, it is 2. Number of phases, now we have to see at this particular point what and all are there. At this particular eutectic point, liquid is also there, alpha is also there, and beta is also there. So we have in total 3 phases. If I write it there, P will be 3. Let's write 3 plus F will be equal to the 2 plus 1. We can see they got cancelled, and F, degree of freedom, is equals to 0. Whenever we are talking about the phase diagram, what variable we consider? We consider the variable as the temperature and the composition. Degree of freedom is saying that we don't have any more choice. you cannot vary the, if you're talking about the eutectic point, you cannot anymore vary the temperature and you cannot anymore vary the composition. Okay. Very good evening to all. So right now we are discussing about the eutectic system. So F is equals to 0 here. So this point will remain fixed. No matter what, in what way A and B I am mixing, if I go to the 58%, I will get this particular point. Other, I'm not getting any point, invariant point, right? So this is the entire thing which we have discussed about the eutectic system and eutectic reaction. Is it clear, Omkar?
Yes, sir.
Great. Okay, so now these are the list of the things. Now let's move ahead. We discuss about the eutectic, hypoeutectic, and the hypereutectic alloy. This also we have discussed. This phase rule we have discussed. It can be help to find the degree of freedom. And at the end, we discuss about the iron carbon diagram. Okay, which professor has drawn. I always prefer this particular iron carbon diagram. And I'll tell you one thing that as a metallurgist or as a material science, we all should be aware about this iron carbon diagram along with their values. What is a composition? What are the list of the reaction that is happening in a invariant reaction? That is peritectic, eutectic, and eutectoid. Three invariant reactions are there. Okay. With the time, we will get familiar with this particular phase diagram. Okay. Now, before I start solving the questions and which will be helpful for you in for the completing the assignment. Before that, I would like to ask you, do you have any other doubt in the list of the concept that has been covered? One thing, feel free to interact with me. You can also unmute yourself, or you can also write in the chat box. I will be happy to respond to you. Okay. Great. Seems like there is no questions. If there's any time at any moment of this particular discussion you feel like there is any doubt is there, please feel free to put in the chat box, or you can also unmute yourself. Okay, great. Let's move to the next part. Since there is no questions, let's discuss about this particular question. Question number 1. Identify the peritectic reaction. No. So among this peritectic reaction, liquid is converting to the alpha and it is giving to the new composition of the liquid. B, liquid is converting to the alpha and beta. Liquid is reacting with the alpha and it's forming the alpha itself. And here the liquid is reacting with the alpha and forming the beta. Among all these 4 options, what do you think? Which one is the peritectic reaction? This thing we have discussed in the class. That's peritectic. Sayak. Yeah. So Sayak has answered that option A is the right answer. What about the others? So let's discuss about all the invariant reaction that we are aware about. Okay. So see, these are the 3 invariant reactions that professor has taught us: peritectic, eutectic, and eutectoid. Omkar is telling that the option D is the right answer. Okay. Very good. Any more? Okay, great. Okay, now we can discuss. So let me write what we have discussed about the eutectic, eutectoid, peritectic, and then we can also discuss about the monotectic. I know that it's not been discussed in the class. It's not discussed in the class, but still, let's have a look on that. Eutectic, we all know liquid is there. It is converting to the alpha and beta. Sayank, yeah, very good. So Sayank has also told the option is D is the right answer. That's great. Option A, we'll discuss what is option A. Eutectoid. Whenever you discuss about the eutectoid, the things will be that will be interacting in the system will be the solids. So here in the eutectic, liquid is converting to the two solids, two phases of solid. For the eutectoid, we can answer it's a one solid is converting to the remaining two solid. Alpha is converting to the beta and gamma. Peritectic. In peritectic, what happened? We discussed that in the, for example, one of the very important reaction that is happening in the iron carbon diagram here. So what we have observed that in the peritectic case, a delta iron was there. It was interacting with, it reacted with the liquid and it gave rise to the gamma. I should not use the word reaction, it's a transformation. So now here, one solid, let's say, if I take the Greek word from the iron carbon diagram itself, so delta is reacting with the liquid and it's giving rise to the another solid, let's say I am writing the gamma. One can also write alpha is reacting with the liquid and giving rise to the beta. There is no difference between them. Okay, so I was going to say something. Invariant reaction we should always write in the two-way direction because we don't know whether we are cooling or whether we are heating it up. Okay, so if I'm heating, so what will happen? For example, the case which we discussed. Let's discuss about this. It's a eutectic reaction happening. Liquid is converting to the two solids, alpha and gamma and cementite. If I'm going from liquid to the, if I'm going from high temperature to the low temperature, in that case, liquid is transforming to the gamma and application. If I'm going from the, if I already have this particular thing, and now I'm making it liquid, I'm heating it up, so then I'm going in the reverse direction. And since we are talking about the equilibrium, this it will always be there. Now, this part, monotactic, that we have not discussed. You can see it's not there in the phase diagram, in this iron carbon phase diagram. But in the couple of phase diagram, you will be able to see that monotactic is also there. So the first option which we are writing, liquid 1 is converting to the alpha and giving rise to the liquid 2. So now you might ask that what is the difference? Both are the liquid, right? They should be miscible, they should form one single phase. The thing is that the composition of the liquid and the composition of the liquid 2 will vary from each other. The first reaction which we discussed, it's a monotactic. The second one, we know that it's a eutectic. And then this is not the reaction that we not discussed, it's not the reaction, it's just one of the transformation where liquid is converting to the alpha. And the last one, liquid is reacting with the alpha and giving rise to the beta. This is our required answer. It's a peritectic. Any doubt in this, guys? Please let me know. We can have a discussion. If not, we can move ahead to the next part. Great.
No, sir.
Yeah, great. Let's move ahead to the next part. Anyone try to answer this question? It's very easy. The phase diagram can predict. Just for the sake of simplicity, more than one answer can be the right. The phase diagram can predict the phases present at the equilibrium, the composition of the phases present at the equilibrium, the metastable phase is present, the relative amount of phases present at the equilibrium. A, B, and D. Great. So Gitu has answered. The answer is A, B, and D. That's right, Sam. Option D is the right answer over here. One thing we have to be see from this particular question that whenever we are discussing about the phase diagram, we are in the equilibrium state. Metastable states, for example, martensite, that is not stable, that is not in the equilibrium. So we are not going to discuss about that in the phase diagram. Phase diagram will not contain the information regarding this. So for example, let's go with the first one. The phase is present. One phase diagram is given to us. We can easily answer what are the phases present over here. We can say that okay, it's a alpha ferrite is there, cementite is there, gamma is there, like gamma iron is there, and that like austenite, and the liquid phase are over here, and this consists of the liquid and the cementite. So we have the entire information about the what are the phases that is present. Second, the composition of the phases present and equilibrium. We can also find the composition of the phases. How we can find that? We can find it using the thing we have learned. Can anyone guess? We can find
Tie
it.
line.
Very good. Good, Omkar. Yeah, it's a tie line. See, by drawing the tie line, here it's alpha. So alpha and liquid is there. So you can just go to its x-axis corresponding, and you will find what is the composition of the alpha phase. Liquid. Then you can just go to the x-axis of this, and you can find the composition of the liquid. So it doesn't matter. So I can take any particular point. For example, let's at this point, I want to find the composition. So we know that what are the phases present is the alpha and the liquid, and I will just simply draw a tri line, and I can find the what are the composition of the each of the phases. So B is done. Metastable state, we don't get the information regarding that. The last one, the relative amount of the phases present. Right. So for example, let's discuss about this itself. So my phase, someone gave me the point like at this particular composition and this particular temperature, what are the phases? We got to know that alpha is present and liquid is present. Our question is that what is the fraction of alpha and what is the fraction of the liquid over here? One thing we are aware that summation is 1. Only these two phases are only present, so their addition should be equal to 1. Now how we can find? Tie line is used to find the composition. Any idea what rules should we apply to find this fraction of the phases? It is nothing but a lever rule. For example, if I want to find the liquid phase, the fraction of the liquid phase is over this side, right? So what I will do, I will take this much of the length and I will divide it by the entire length of this particular lever. Okay. So for example, I had this phases. Here is a liquid, here is alpha, and this is my point at which I want to find. What I will do, let's say this A, B, and C are there. So what I will do, if I want to find the fraction of the alpha, I will just do B, this length, B minus A, divided by entire length, that is C minus A. This is the fraction of the alpha. Similar way, we can find that the fraction of the liquid. That can be done by, since liquid is this side, we'll take the opposite arm, that is C minus B, this much. We'll divide it by the entire length. The entire length is again C minus A. That's great, yeah. So Guido has wrote, it's a lever rule. So we'll remember that in order to find the composition, we will use tie line. And if we want to find the fraction of the phases, we'll use the lever rule. Okay guys, let me know if there is any doubt in this. If there is, we can discuss. If not, let's move to the next question, question number 3. Okay, great. Since there is no doubt, let's move to the question number 3. The question says, in a binary alloy, the number of phases present in equilibrium at the eutectic point is, and at the eutectoid point is dash. Number of phases present in the eutectic point and at the eutectoid point. We want to find the number of phases. How we can do that? See, I know what is happening in the eutectic reaction. We all just discussed that liquid is transforming to the alpha and the beta. So at the eutectic point, all this invariant reaction, all the phases that is present in the invariant reaction will be there. All phases, that is 3 phases, will be present. So in the case of eutectic, we got that how many phases are there? Liquid is also there, alpha is also there, and beta is also there. So we can say 3. What about the eutectoid? What is happening at the eutectoid? Eutectoid, alpha is transforming to the beta and gamma. How many phases are there again? The number of phases again is 3. It is alpha, beta, and gamma. All the 3 phases will be present at this particular eutectic point. So it's 3 and 3. So Omkar, the answer will be C, right? The number of phases present at equilibrium in the eutectic point, it will be 3, and the eutectoid point will also be 3, right? Okay, shall we make the question a little bit interesting? Let's first of all, is this clear? Okay, let's have this phase diagram. Now my point will change. Let's first write, let's say this is alpha, this is beta, this is liquid. Do you have black pen? Here we have liquid plus alpha, here we have liquid plus beta, here we have alpha plus beta. These are the things we have. Now my point is, for example, in the last question we discussed about the eutectic point and the eutectoid point. Now my point is this, and now my point is this. Our question remains same. This is, let's say, point A, and this is point B. So for A and for B, number of phases we have to find. At equilibrium. At point A and the point B, we have to find the number of phases. Can anyone quickly answer this? It's very easy, right? We just discussed about it. Point A is nothing, right? It's simple. Point A consists of again, it's a eutectic reaction only. So number of phases that is present is 3. Now what about this point B? What are the phases do we have? At this point we have alpha, and we have alpha plus beta. Right? Yeah, that's right. It's the 3 phases are here. At point B, now our question is that what is happening at the point B? See, let's say I'm cooling. What is happening? The alpha is transforming to the beta. Right. So at this particular point, we have alpha and we have beta also. Above this point, we only had alpha. Below, we have alpha and beta. So here, at this particular, this is the equilibrium between these two. Okay, whatever the border we are drawing now, that will be the, like both the phases across the border which is there will be present. For example, this border. This one. What we have is, here liquid we have, here alpha we have, here will be alpha and liquid. Okay, so this will be always there. So at this particular border, both the phases, like alpha and the liquid will also be there. At this point also, beta will be there, liquid also be there. At this point also, liquid will be there and the beta will be there. And now at this particular point, we have beta and we have alpha. At B, it should be 3. Now, why it should be 3? We have to think about that. What is happening at the B? What we have is alpha. Here what we have is, on this border we have alpha plus beta. Alpha to alpha plus beta. Yes. See what is happening here. Liquid was there. Liquid was transforming to the alpha at this particular thing. So whatever is the leftover liquid is nothing but the leftover, the initial liquid itself. It's like entire transformation has not been completed yet. Let's say we had 100% liquid. and out of that 50% got converted to the alpha. So 50 got converted, right? What is left over? Left over is nothing but 50% liquid. It is left over only. It is not different. It is no long. It's not different. If it will be different, I will write as like liquid 1, liquid 2. But we can see there is no liquid 1 and liquid 2 over here. Liquid here, liquid here. Similarly, here also, what we are seeing that alpha is transforming to the beta. Okay, at this particular point now, like if I go across this line, alpha, we can see that is transforming to the beta. Now the entire will not transform. Certain extent will be remain. So whatever is left over will be alpha. So here also we have alpha. Here also we have alpha. So they have something in common. Alpha is common in both of them. What is additional is there? It's a beta. And this is in the equilibrium. Similarly for here also, this particular point, we can see that the beta is transforming to the alpha. And leftover beta is here. Okay. So what we can see here is the beta is there. Here also alpha and beta is there. So beta is there on the both the side. So beta we have already counted. What is left over is the alpha is also there. So we have at this particular point we have 2. Okay, so this is 2 phases that we are having. So that's why, is it clear? So Gitu has asked about this. Is it clear, Gitu, that the answer will be the number of phases should be 2? Great. So here we can see that number of phases is 2. Now let me change. Shall we change the question again? Let's take one more question. We'll quickly do this. Liquid, beta, alpha, alpha plus liquid, beta plus liquid, alpha plus beta. Let me mark the point. One, 2, 3, 4. These are the point at which we want to find the number of phases at the equilibrium. Can anyone quickly tell me the answer for the 1.1? How many phases will be there? It will be 3, right? Yeah, great, sir. At 1 we have 3 phases. What about 2.2? Omkar and yeah, the number of phases here is 2. Yeah, great. So we have alpha, we have beta over here. The number of phases is 2. 0.3.
So 2 phase.
2 phases are there. Very good. What about the 0.4?
Only 1 phase.
Only
Alpha.
one phase is there, alpha. So we can write 1. Why it is important to us? Because we know that we write the Gibbs phase rule. For this particular phase diagram, what is not changing is the number, is the composition. Sorry, it's a component. Component is, let's say here A and B. So component will always remain 2. So if we want to find the degree of freedom, what is changing is the phase number of phases. And that's why knowing the number of phases at each of the point is very important to us. Okay. Now let's move to the next part. I hope it's clear. It's clear to everyone. We are able to answer these questions. Now let's go to the question number 4. If any doubt till now, let me know. Okay, seems like there is no doubt. Great. Now let's move ahead. In a binary alloy, which of the following phase region can be present across the solver's line? We have to we need to know about the solver's line. First of all, binary alloy. Which of the following phase region can be present across the solver's line? We have already discussed about it. It's nothing new. The solver's line is nothing but it's this line. This is known as solver's line. This is a solvus line. This is a solvus line. So now let's discuss about this. Yeah. We drew a diagram. The solvus line is, sorry, it's D. Great, good. So option D is the right answer over here. The solvus line is the one we can see over here. This is the solvus line. If we don't know about this, then we will not be able to answer it. So this is known as solvus line. Across which one solid and the other two solids are present. So we can see that the beta is the one is common on both the sides, and the beta is transforming to the alpha. Liquid transforming to the liquid and alpha? No, it's not. It's the liquidus. It's not the solvus. Okay, this is a liquidus. This point, this lines are the liquidus. So with that, we can say that the one solid will be there. It will transform to the another two solid. This is what? This is nothing but eutectoid. Alpha is transforming to the beta and gamma. This is our solvus line. Great. Any doubt? Let me know. If not, let's move to the next part, question number 5. The questions can be a little bit tricky, but once we understand that, what is the essence of the question, then we will easily able to answer that. Now, let's move this part. Under equilibrium condition, which of the following are true for the both hypereutectoid and the hypereutectoid steel at 100 degrees Celsius? Right. So these are the list of the statement that is there, which we have to verify that this would be valid for both things, hypereutectoid as well as the hypereutectoid. One important thing, they are talking about the equilibrium. Since they are talking about the equilibrium, we can use the phase diagram. Temperature they have specified 100 degrees Celsius. Okay, they are talking about the hypo and hyper. But what is hypo and what is hypereutectoid steel? See, we know this invariant reaction. This invariant reaction. Point 8. This is eutectic. This is eutectic composition. Anything below this composition will be the, what we can say, it will be the hypoeutectoid. Anything above this composition, we can say somewhere this region, it will be hypereutectoid steel. Okay. So this also will be there and this will also be there. Now we are talking about, so we got to know that what is eutectic steel. Oh, sorry, what is eutectoid steel? What is hypoeutectoid? That is this region. Anything below the eutectic, anything below 0.8. What is hypereutectoid? Anything above 0.8. We got to know this much information. What is eutectic and what is hypoeutectic, hypereutectic and hypoeutectic. Now let's go. Let's see for the option A. Alpha ferrite will be present. We can see. Better I draw here. The same thing I will draw over here. This is going there. This is austenite. Austenite is transforming to the, this is eutectoid composition. That is 0.8. Here we have the alpha ferrite. Here we have alpha and gamma. Here we have gamma and Fe3C. And at the bottom, what we have is ferrite and cementite. Okay, clear. So now what we can see that gamma was there, it got transformed entirely to the ferrite and cementite. In the both the cases, P, alpha ferrite will be present. The P is saying that the alpha ferrite will be present. So we have alpha ferrite in both the cases. That is true. From the phase diagram, we are able to answer this. Second one, cementite will be present. Cementite is also present. Okay, so throughout this particular range, we have alpha ferrite and we have cementite. Austenite will be present. Option D. No, austenite will not be there. Austenite has already transformed because we are around this particular temperature 100. At this temperature, entire austenite has been already transformed. सर मैं NPTEL का लेक्चर ले रहा हूँ, थोड़ी देर में आऊँगा. Okay, so the alpha and Fe3C we have. So only the right answer is P and Q. So here we can write option C will be the right answer over here. Great. Let's move to the next question. Question number 6. It's very easy. The relative amount of phases present at the equilibrium can be found using. So which of the things we should use to find the relative amount of the phases present? We have already discussed. If we want to find the fraction of the phases, we'll use the lever rule. While if we want to find the composition of the phases, we'll use the tie line. So here the right answer will be the option B. Right. Let's move to the next part, question number 7. If any doubt, let me know. Let's move ahead. This is the question number 7. Find the phase fraction of the alpha ferrite in a plain carbon steel with 0.1 weight % carbon. At the temperature just below this, take the eutectoid composition of a steel as a 0.8. This is what we have to find the fraction of the alpha phase. So we have phase which is alpha and we want to find its fraction. It's very clear to us that what we have to do is we have to apply the lever rule. Now let's see. We are talking about the just above the 7 to 7. That is, we are just above the what we can say that eutectoid reaction. Over here. This we already know. It's a see here. We already know this point is nothing but 0.02. It's a 0.02. This we know that 0.8 that is given to us. What we have to find, this is 727 degrees Celsius, which is just which is the eutectic temperature. Now we are just above this and our composition is 0.1 around here. We are at this particular composition. This is 0.1. Our aim is to find the fraction of alpha phase. What are the phases that is there? Gamma. If I complete this is alpha. So what we have is alpha plus gamma. Alpha is this side and gamma is this side. So what we'll do, we have to find the alpha fraction. So we'll take the opposite arm. Opposite arm is this one. That is nothing but 0.8 minus 0.1. We'll divide this by entire arm, that is 0.8 minus 0.02. Now we can easily find this. With this we can compute the answer. Okay, simple mathematics. So with that I will leave this to you. Let's move to the next question, question number 8. If there is any doubt, let me know. Question number 8 says, If copper nickel alloy with a fixed composition is cooled from its liquidus to its solidus temperature, what happened to the phase fraction of alpha? Okay. We know copper and nickel diagram. Copper and nickel phase diagram, they form the isomorphous phase diagram. Liquid alpha, here it will be liquid plus alpha throughout this region, throughout this range. Question says the composition is fixed. Let's say we are fixing the composition also, let's say this composition. Cooling from its liquidus, this is liquidus and this is solidus. Cooling from its liquidus to the solidus temperature, we are varying from this temperature to this temperature. What happened to the phase fraction of alpha? How the alpha is changing? Very good, Sam. It's the option A, it will increase. Initially we had the entire microstructure was liquid, but once we went somewhere, let's say in between, what we'll get, the microstructure will be liquid will be there. Along with that, the solid phase of alpha will also be there. So it has increased. Now if I move to the entirely solidus, what we'll get is a microstructure like this. Okay, no liquid will be there. Very good. So option A is the right answer over here. If any doubt, let me know. If not, let's move to the next part, question number 9. In the iron carbon phase diagram, which of the following is /R are a solid solution? We have austenite with the present by gamma. This is alpha ferrite, this is delta ferrite, and this is cementite, Fe3C. Among this, which are the solid solution? This is the question. Any answer? Any? Can anyone tell? A, B, and D. Very good, Sankar. It's the option A, B, and D. Cementite is a, what we can say, it's a intermetallic. These are the, among the solid solution also, this alpha, delta, and gamma, they are the interstitial solid solution. Solid solution of carbon will be there at the interstitial site, and the structure will be made by the iron. Right. So Gitu has told that option A and C. We know that cementite cannot be the answer because it's an intermetallic. Remaining all the austenite, ferrite, and both the form of the ferrite, alpha and delta, they will be the, what we can say, they will be the intermetallic solid solution. Sorry, interstitial solid solution. With that, we have completed the question number 9. Any doubt, let me know. If not, let's move to the next part, question number 10. This is a question. For a constituent point in two-phase region of a ternary alloy, constant pressure, there are dash degree of freedom. We need to find degree of freedom. We know only one way by which we can find the degree of freedom is that by the Gibbs phase rule, P plus F is equals to the C plus 2. This 2 is for the temperature and the pressure, but we already, the information is given to us, the pressure is constant. So we'll use the P plus F is equals to the C plus 1. Few more information is given. Number of phases is 2. So P is 2. Ternary phase, ternary alloy. It's a ternary alloy. It means that the number of components are 3. So what we can say, C is 3 plus 1, P is 2 plus F. What we can say from here, F will be equal to the 3 plus 1 minus 2, which is 2. So in this way, we can find the answer like option C will be the, C is the right answer over here. So whenever the questions regarding the degree of freedom is coming in the questions, we have to use the Gibbs phase rule. And we need to be aware that what is C and what is P over here. If you are correctly able to find the C and the P, then the question will be done. One more important thing, this is sometimes hidden, whether it's a 2 or it's a 1. So by reading the question, here I wrote that it's a constant pressure. But someone can tell that it's a binary alloy, or let's say someone is telling that iron carbon diagram. So we know when we are talking about the iron carbon diagram, we already fixed the pressure. So these are some hidden information will be present in our questions. Okay. So among this and this, we have to decide which one to use. Okay, this is the question number 10. Any doubt in this? Let me know. If not, let's move to the next part, question number 11. We are left with 4 questions. Steel typically contains what percentage of carbon? We have entire phase diagram with us. Among this, yeah, Sayank has answered, it's between option A, between 2 and the 4.3. It's not correct, right? We know. In the class, it has been discussed that this. Yeah, that's right. Option B is the right answer. That is less than 2%. So less than 2% is the steel. And more than 2%, it's a cast iron. This is the basic information which we have to be aware of. Okay. One more question people usually ask, that why the iron carbon diagram is only till the 6.67. Why you are adding only the 6.67% of the carbon? Why not more than that? That is the reason we have already aware that it doesn't has any application, because the material will be extremely brittle. These are the type of the questions one can ask in the interview. Okay. Now let's go to the next question, question number 12. Very simple question. In iron carbon diagram, which of the following invariant reaction occur at the 725 degrees Celsius? At this temperature, which are the invariant reaction that is happening? Option C, very good. It's a eutectide, right? So it is over here. We know that this is the reaction which is having around 725 root, very much close. Yeah. So we know that it's a gamma is transforming to the alpha, beta. Sorry, I should write the alpha and cementite, ferrite and cementite, when we are talking about the iron carbon. Very good. Let's move ahead to the next question, question number 14. Sorry, question number 13. It's a true and false type. Let's try to do one by one. The number of degree of freedom increase as the number of phases in the equilibrium increases. Will it be true or false? The question is said that f number of degree of freedom, if it increase, then the number of phases, like the number of phases increase, will lead to the increase in the degree of freedom. Gitu has told that it's a false. What's the reason behind that? We know about the Gibbs phase rule. P plus F is equals to the C plus 2. Yeah, very good, Sam. It's a false. Number of phases, let's shift that number of phases, that is P, onto the other side. If F will be equal to then C minus of P plus 2. If I increase the number of phases, it's in the negative, so it will decrease the degree of freedom. If P is increased, F will increase. So they are in the reverse, opposite to each other. It's a false. Next part. In a single phase region, both the composition and the temperature can be independently varied. That is, they are telling that temperature and the composition independently vary. It means that the number of freedom, the degree of freedom, they are telling it's a 2. The composition and the temperature. The question is saying that if the degree of freedom will be 2 in the single phase region. Let's say we are talking about the binary, right? Okay, I should complete the question in the case of binary phase diagram. So let's say take a diagram. Let's take a phase diagram. Before that, please try to answer if you have already got the answer. Let's say we are talking about the isomorphous liquid alpha, liquid and alpha. Okay, copper and nickel. Let's try to apply this phase rule. Let's say single phase they are talking about. I can take liquid also. I can take alpha also. Anyone is fine to me. So let's say I'm taking the alpha and at this particular point. So what I have in this region, the number of phases is P is 1. And here again I will use the 1 only because the pressure is constant. So number of degree of freedom is F, and it will be equal to the what is C? C is 2. That is copper and nickel we have 2. The 2 components are there plus 1. This one. So F is equals to the 2. So it means that we can vary both of them, composition and the temperature. And the answer is true over here, right? It's a little bit tricky. The question was a little bit tricky, but we are able to solve. It just we have to decode that the question is related with the Gibbs phase rule. Let's move to the next part. The eutectic reaction is an example of invariant reaction with 0 degree of freedom. Is it true or false? Very simple, right? Eutectic reaction is an example of the invariant reaction. The thing is that 0 degree of freedom. At the eutectic point, at the eutectic reaction, the degree of freedom will be 0. It's true, right? Very good. Very good, Sank. So you to see that we have, again, we will apply the same thing. We know, let's say so right now we are talking about the eutectic. So eutectic liquid is converting to the alpha and beta, and we know that the number of phases here is 3. We discussed this multiple times. So this is 3 plus F, and component we know it's a 2 plus 1. So we can see here that F is equals to 0. So this is the right answer, option C. Let me know it's clear. If there is any doubt, we can discuss it. If not, let's move to the next part, question number 14, the last question. One can easily answer this. We have already discussed. I just changed the alpha to the liquid. I should have make one different questions. What do you think? What will be the composition of the liquid phase as a solidification progress? Will it increase or will it decrease? Or it will remain constant? The fraction of the liquid phase, it will decrease. Very good. Okay. So these are the list of the questions which I have planned to discuss in this class. It will be helpful. Like a couple of questions are there which we have just took it in the different way. So you can find that in the assignments, the questions are more or less similar nature. And this was the list of the things that I wanted to cover. If there is any doubt from your side, please let me know before we wind up. Also, if you are facing any difficulty in the assignment, let's say you have some confusion in the solution or in the answer, you can also discuss that. Weeks 5, week 4, so on and so forth, whatever week has been covered, that we can discuss. If there is no doubt, we can wind up today's class. One more thing, today I saw that I was occupied on the Saturday. That's why I was not able to keep the meeting on Saturday. But today I saw that the number of people are comparatively, they are more. So I would like to ask you, do you want me to continue on the Monday or Saturday 3 to 5 is fine? I'm comfortable with both of them. So accordingly, I will write a mail and we can have a next meeting on this particular week 8. Okay. Okay, seems like there is no doubt. Yeah, please go ahead.
I have a question in iron carbon diagram.
Yeah.
The concentration of carbon present in alpha phase is 0.025, but in austenite phase, the austenite region, there is a concentration of carbon is 2.1%. How it will happen? Sir?
Can you, like, you're talking about this is 0.02 and here it's
Uh,
2.1.
2
That is the question, right?
uh,
Why it is varying? Is it that the question?
Bad.
Very good. So see, this question, it's very deep question, and we have it can be answered in a way of the structure. When we are talking about the alpha ferrite and when we are talking about the gamma ferrite, gamma, that is austenite. The structure is BCC. The structure is FCC. When you will, I think we have already discussed about the void size in the FCC and in the BCC. You will find that in the case of FCC, you will be able to occupy that void, the carbon void will be more effectively occupied. The strain, see, why something is not like, why the alpha ferrite is not able to take more than 0.02. The reason is simple. So, for example, you're talking about this at 0.08 also. So, why it is not able to take more than that? It is not able to take more than that because the thermodynamics, it's not allowing it. What thermodynamics says? Thermodynamics says that if the stress or the strain is more, if the thermodynamically it is not stable, then it will not be able to take. For example, if I am trying to put 0.01% carbon in the alpha ferrite, it will reject remaining part and it will form the Fe3C. It will not go more than this at a particular temperature because its structure is like that. The BCC is not allowing it. They both are having different structure. You can also see in the case of delta ferrite, again, the composition is the amount of the carbon that it's able to take. It's low. So it's depend upon the structure, it's depend upon the void size, and also it's depend upon the temperature. So these are the factors that is there. Okay. So the maximum amount of this question, the question which is asked, it's beautiful question. The maximum amount of carbon that can be dissolved in which phase, whether it's alpha ferrite, austenite, or the delta ferrite. The answer will be the austenite. And what amount? It can go to the 2.1%. That is the maximum. Okay, we cannot move more than that. If we go more than that, austenite will reject. See, if I'm going more than that, austenite will reject Fe3C. Will reject the carbon and it will form the Fe3C. Here, ferrite reject the carbon, it form the Fe3C. Here also, if I try to move along this, it will reject. Okay. Is it clear, Sank?
Yes, it is clear.
Any more doubt, Sank? If there is, please let me know.
No doubt.
Great. So with that, we can wind up today's class. If you face any doubt in between while solving the assignment or while studying, you can also put on the Q&A forum. I will be happy to respond to that. So with that, we can conclude today's class and let's meet again. Tentatively, let's meet again on Saturday, 3 to 5 p.m. Okay. Okay, guys.
Thank you.
Yeah, bye-bye.